Hello everyone, I am Kundan and today we will deep dive into super important topic that is asynchronous FIFO design and its verification in SystemVerilog. Here is the content of the slides. First we will see FIFO and its types, then block diagram and control signals, asynchronous FIFO concepts like metastability, synchronizer, FIFO depth. Then we will see design concepts like full, empty, read and write. Then we will see the design code, then SystemVerilog Testbench Architecture, then various test benches for verification, and then finally waveform and its result. Now, what is FIFO? FIFO stands for first in, first out. It is a memory or buffer that ensures the first data retained is the first data to be read. Here is the use cases of the FIFO. FIFO is used in the clock domain crossing, that is transfer the data between the blocks running at the different clocks. It is used in data buffering, a smoothness of data transfer between the producer and the consumer. It is used in the rate matching and in serial communication like in UART or SPI buffering, and in pipeline staging. It holds data in pipeline digital design. Type of FIFO. FIFO is categorized into two types. First is synchronous FIFO and second is asynchronous FIFO. In synchronous FIFO, both read and write operation is done using single common clock, but in asynchronous FIFO uses separate clock for read and write. Now why asynchronous FIFO is needed? Let's say your CPU is running at 1 GHz and your peripheral is running at 100 MHz. How will they exchange data reliably? There is where asynchronous FIFO come in. Let's see the block diagram of asynchronous FIFO. Here is the control signals of asynchronous FIFO. Here is data in, the data to be write. Data out, data to be read. Read enable, write clock for the write clock domain, read clock for the read clock domain. Now we have two handlers, write pointer handler and read pointer handler. Write pointer handler will generate full flag and a read pointer handler will generate empty flag. Write pointer handler will generate two pointers, binary write pointer and gray write pointer. The read pointer will generate two pointers, binary read pointer and gray read pointer. Now we will pass gray read pointer in the write clock domain and gray write pointer in the read clock domain. Now what is this? We will see in the next slide. Here is the control signal that I have already explained. Now what are the key challenges in the asynchronous FIFO? First is metastability, because data crosses clock domains. Second is pointer synchronization. Read and write pointers need to be updated safely. And third is full and empty detection, tricky because clocks are independent. Now what is metastability? Metastability occurs when a flip-flop receives a signal too close to its clock edge, violating setup or hold time. As a result, the output becomes unstable, neither a logic 0 nor 1 for an unpredictable time. For example, see here, this is the setup time of the clock edge and it is the hold time. If some data comes in between this, then it will violate the setup or hold time, and that data will go to the metastable state. Clock domain crossing. Clock domain crossing refers to the transfer of data or control signals from one clock domain to another clock domain, which are running at different frequencies or spaces. For example, in our asynchronous FIFO, both read and write both are working in different clocks. So why clock domain crossing is challenging? Because time is unpredictable, because clocks are asynchronous, signals can arrive mid-transition, leading to metastability, causes glitches, data corruption, functional errors if not handled properly. Metastability solutions. We solve the metastability problems by passing it through two flip-flop synchronizers. Now what is two flip-flop synchronizer? It consists of two D flip-flops. First data is passed to first D flip-flop, then to the second D flip-flop, then we get the stable data. The first flip-flop may go to metastable, but the second flip-flop will capture the stable output safely. Now passing the pointer from one domain to another domain, we use gray code pointer. Why gray code? Because gray code ensures only one bit change at a time. It reduces the chance of invalid transition during the synchronization. It also reduces the metastability. For example, when the value changes from 3 to 4, in case of binary, it changes 3 bits. But in case of gray code, only 1 bit goes from 0 to 1. So it reduces the metastability. Now let's see how it is working. In asynchronous FIFO, we pass the write pointer in gray code to the read clock domain and read pointer in gray code to the write clock domain. Then we synchronize them using two flip-flop synchronization. Write pointer is synchronized into read clock domain and read pointer is synchronized into write clock domain. The question arises why pointers are actually exchanged. Pointers are exchanged between domains to detect the full and empty status. This ensures FIFO does not overflow or underflow during asynchronous operation. Now let's understand the complete picture, how the FIFO is working. For FIFO, we have data in and data out. Data in for write and data out for read. Write enable and read enable. Write clock for write clock domain and read clock for read clock domain. We have two pointer handler, write pointer handler and read pointer handler. Write pointer handler will generate two pointers, binary write pointer and gray write pointer. Read pointer handler will generate two pointers, binary write pointer and gray read pointer. Now, gray read pointer is passed to read pointer handler. Now, gray read pointer is passed through two flip-flop synchronizers to the read pointer handler. Because it is passing from one clock domain to the next clock domain, so we need to pass through the two flip-flop synchronizers to remove the metastability. Similarly, gray read pointer passed to write pointer handler by passing through two flip-flop synchronizers to remove the metastability. Now, here we have write pointer and read pointer. By comparing them, we detect the full flag. And in the read pointer handler, we have read pointer and as well as write pointer. We will compare and we will detect the empty condition. This is the actual diagram. Now, what is FIFO depth? FIFO depth simply means the number of data words the FIFO can hold at a time. Why FIFO depth matters? If we choose wrong depth, that causes serious problem. For example, if we take depth too small, then it will cause overflow and our data will be lost. And if we take depth to be too large, then it wastes area, power and increase latency. So we need a balance, not too big, not too small. Here is a question on the FIFO depth. For example, in this question, frequency of write is 100 MHz and frequency of read is 50 MHz and our burst data is of 100 bytes. Now time taken for one write, it will be 1 upon 100 MHz, that is 10 nanoseconds. Now for 100 bytes burst data, time will be 100 into 10, that will be 1000 nanoseconds. Now time taken to read one data will be 1 upon 50 MHz, that will be 20 nanoseconds. Now in 1000 nanoseconds, byte rate will be 1000 upon 20, that is 50 bytes. 100 bytes of data is coming and only 50 bytes of data is read. So our depth will be 100 minus 50 is equal to 50. Now let's move to the design part of our asynchronous FIFO. Here is the logic for empty and full flags. Full and empty flags are generated using the difference between write and read pointer after synchronization. Now the key idea for finding the empty is that if both the pointers are equal, then we consider that our FIFO is empty. And for full, if write pointer is equal to read pointer with MSB inverted and LSB same, then we consider the asynchronous FIFO to be full. Now let's see the design code of asynchronous FIFO. We have used the parameterized way. I have taken data width as 8, address width as 4. Now for the write domain, we need data in, write enable, write clock, write reset, full flag. For the read domain, we need data out, read enable, read clock, read reset and empty flag. Now we need depth. Depth is calculated as 2 to the power address width, that is 1 left shift address width. Now we declare the memory of our required data width and the depth. Then we need two pointers, write pointer and read pointer. For write pointer, we declare binary write pointer and gray write pointer. Similarly, for read pointer, we declare read binary pointer and read gray pointer. Now here is the synchronized gray pointer for both read and write. Write operation, always at the rate process of write clock or process of write reset, that is we have used asynchronous write reset. When reset will come, then we will make all our pointer to 0. Else if write is enabled and FIFO is not full, then we will store the data in to the required address and we will count +1 to the right pointer binary, and then we convert it into gray. Then we synchronize the read pointer into the right clock domain. That first we pass through first flop, then to second flop. Similarly, for the read operation, at passage of read clock and passage of read reset. If read reset, then we make all our pointer to 0 and data out will be 0. If read enable is high and if it is not empty, then we take out the data from the required address and we count +1 to the read pointer and make gray pointer from it. Then we synchronize the right pointer into the read clock domain. That first we pass it through first flop, then through the second flop. Now we will convert the required gray to binary. Here is the function. Here the pointer we receive in gray pointer, first we convert into binary, then check the full and the empty condition. Now let's move towards the Testbench using the SystemVerilog. SystemVerilog supports powerful features like classes, randomization, coverage, assertion, and oops, all of which make Testbench scalable and reusable. Here is the Testbench architecture. It consists of generator, transaction, driver, interface, duty, monitor, then transaction, and a scoreboard. Now I will explain each term. Generator generates a stimulus and send it to the driver using transaction. Transaction is just like a packet. It consists of data to be sent and data to be received. Then driver send it to the interface. It is just like a helping hand and it passes to the interface. Now come to monitor. Monitor is a passive element and it only observes the output from the interface. And it passes its result to the scoreboard using transaction. Now scoreboard compares the actual result and the expected result, and it will tell us that our test case passed or failed. We will move to its code one by one. Here is the flow diagram of our architecture. Generator generates the stimulus, send transaction via mailbox to the driver. Driver drives interface signals. Then it goes to monitor. Monitor reads interface signals, sends observed transaction via mailbox to the scoreboard. Then a scoreboard computes expected and compares with the duty result and tells us that our test passed or failed. Now let's move toward the code. Here is the interface code. Interface FIFO if. We have used the parameterized way. I have taken data way to be 8 and then write clock, read clock. Then here is the DUT input and DUT output. Data in, read reset, write enable, and data out, full flag and empty flag. Then I use modport. Modport is used to provide direction and end interface. Here is the transaction class. Transaction class consists of data, write enable, read enable. We make it ran because we will use randomization. And then here is the expected data. We make constructor, default constructor, data is set to be 0, write enable to be 0, read enable to be 0, and expected data to be 0. And here is the display statement to display which class is currently running. Then we make a clone of the transaction which is used in the monitor, and we make a compare function which is used in the scoreboard to compare the actual data and the expected data. Generator class. Generator class consists of two modes, 0 and 1, which is represented by bit random mode, 0 for user defined and 1 for random. Then we need queue for the user defined, mailbox to transfer transaction from the generator to the driver. We by default take number of transactions as 10. Here is the constructor. We initialize mailbox and take random mode as 1 by default. Here is the task to add the user defined transaction to the queue. Now here is the run function. Now we first initialize the transaction. If it is random mode, that is 1, then we repeat number of transactions, that is 10. Then transaction is created by tr.randomized and we put the value generated into the mailbox and pass it to the driver. If it is not random mode, that is it is user mode, then we take out data from the queue and put it into the mailbox and we pass to the driver mode. Now we will see the driver part. Now the data comes to the driver. Driver will send the data to the interface. Now let's see its code. Class driver, it will instantiate interface and the mailbox. Here is the constructor where we instantiate the mailbox and the interface. Here is the run task where the driver takes data from the mailbox by using the command .get. Now there are two operations, write operation and read operation. For write operation, if read enable is 1, then it will check if FIFO is not full and FIFO is not at write reset, then it will make the read enable as 1 and data in as transaction.data. It will simply pass the data from the transaction to the interface. Now at the next passage of clock, it will make the write enable as 0 and display the statement. For the read operation, if read enable is 1, then after some delay, it will check the FIFO is not empty and FIFO is not at read reset, then it will make read enable as 1, then at next passage of clock, we will make read enable as 0, then we will display the statement. Monitor observe the data from the interface and pass it to the scoreboard. Now let's see the code for monitor. Monitor, required interface and mailbox. Here is the constructor where we initialize interface and the mailbox. Then we run monitor write and monitor read in parallel by using the fork join. Here is the task for the write and here is the task for the read. For write, task monitor write, we make transaction tr, then run a for ever loop. Then at passage of clock, if write is enabled and memory is not full, then we make a new transaction and make write enable as 1. Then we put the data from the interface to the transaction and put the transaction in the mailbox so that it can pass it to a scoreboard. Now for read, we make task monitor read, then we declare transaction tr, then we run forever loop. Then at the next passage of clock, we check if read is enabled and FIFO is not empty, then we make a new transaction tr is equal to new and make read enable as 1 and take the data out from the interface to the transaction and put it into mailbox so that it can pass into a scoreboard. Now let's see the scoreboard. Now in the scoreboard we compare the expected data and the actual data and it tells that our test is passed or failed. Let's go through its code. Here class scoreboard, then we take parameters data width is equal to 8, then we take the expected Q for write the expected value and mailbox that we receive from the monitor, and here is the constructor. Now task run, we declare a transaction tr and then we run forever loop, then we take data from the monitor. Now there are two operations, write operation and the read operation. For write operation, we push the value to the expected Q so the data can be compared. Now if we read operation, read is enabled and write is not enabled, then if expected Q is greater than 0, then we compare the value from the mailbox and the expected Q. If it is not equal, that means our test case is failed. If it is equal, that means our test case is passed. If the Q is not greater than 0, it is less than 0, it means it goes to underflow, read occur with no expected value. So here our scoreboard tells that our test case is passed or failed. This is our top module where we include all the modules like interface, transaction, generator, driver, monitor, scoreboard and environment. In top module, we take parameter data with a 8 and address with a 4. Then we instantiate the interface. Then we generate the clock for write clock and the read clock. Then we connect our test bench to the DOC, and here is the code for wave generation. Now let's see the different test plans to validate our Asynchronous FIFO. For that, I use 9 test plans: reset test, then one write, then read test, multiple read write test, overflow condition, underflow condition, random write and read, wraparound test, apply reset at middle, simultaneous write and read. First is reset test. For reset test, we make write reset as 1, then read reset as 1, and write enable as 0, read enable as 0, data in as 0, and after some delay, we make write reset as 0 and read reset as 0. Now let's see it waveform. Here we make write reset as 1 and reset as 1, then after some delay we make it 0, and our FIFO is empty. Empty is 1 and full is 0. Now our second test plan is to write one data and then read it back. So here we make write enable as 1 and read enable as 0, then we take data as 42. Then we read it back by making write enable as 0 and read enable as 1. Now let's see its waveform. Here we write one data and read it back. Write enable is 1 here, so it will write here, and here read enable is 1, so it will read. Multiple write and read test. For that, we take a for loop and write 4 data to our FIFO and then read it back. Let's see the waveform. Here we have written 4 data 0, 1, 2, 3, 4 and then read it back. Then our data is coming correctly. Overflow test. Now our FIFO is of size 60 only. If we write extra, then it will not accept it. Now let's see. Here I have used for loop and I have written 20 data. Let's see in the waveform. Now in waveform, after 16, right, our FIFO is not accepting any further data. Initially empty is 1, then it goes 0 after write, and full is 0, it goes 1 after 16 write. Underflow test. In underflow test, we attempt to read even if our FIFO is empty. For that, I have first written a single data, then we read 5 times. Let's see the waveform. I have written one data. Even if I try to read 5 times, now our FIFO is empty, it will not show any data. So observation is empty is 1 initially, then it goes 0 after 1 write, then 1 after read, then remain 0 after more read also. So our underflow test is also passed. Random write and read test. Here we randomly generate the read enable and the write enable. If write enable is 1, then we randomly generate the data between the range 0 to 255, and if write enable is 1, then we read the data. Now let's see the waveform. Here we randomly generate the read enable and the write enable. If write is enabled, then we are randomly generate the data between 0 to 255 and write it to the FIFO, and if read is enabled, then we read it. Then data is coming out correctly. Wraparound test. For checking the wraparound test, first we completely fill the FIFO. Then we read half of it. Then we write 8 more items. Then we read the remaining item. Let's see its waveform. Here we first completely fill the FIFO. Then we read half of them. Then we again put 8 data to the FIFO. Then we again read it back. Now our pointer is wrapping around correctly and giving the data correctly. That is, first data is the first data to be out. Apply reset at middle. In this test, we have written some value in the FIFO and we apply reset at middle. Let's check its waveform. Here we have written some value in the FIFO. Then after some time, we apply the reset as high. We can compare its correctness by checking the empty flag. First, it is 1 when FIFO is empty. When we write some data, then it goes to low. After applying reset, then empty again goes to high. It implies that it is working fine. Simultaneous write and read test. In simultaneous write and read test, we make both write enable and the read enable high at the same time. Now, in my case, I have written some data to the FIFO. Then we take another for loop where I make simultaneous read and write. Let's see its waveform. First, I have written some data to the FIFO. Then I make simultaneously read enable as high and the write enable as high. But the data is coming out correctly when the read enable is high. That is, the first data to be written is the first data to be out, and the data written is goes to the correct place also. Thank you everyone. Please like and subscribe to the channel. And if you have any doubt or query, please comment in the comment section.